Hello, and welcome to From Mesh Generation to Adaptive Simulation, a journey in Julia. My name is Andrew, and I will be your guide on the journey. Before we begin, let me acknowledge some helpers that got us here. There's the main developer of HOHQMesh, David Capriva, my fellow collaborators on Trixi, Jesse, Gregor, Hendrik, and Michael. And I want to highlight some extra help we had with Trixi from Erik, Christoph, and Andres, specifically for shot capturing and adaptive refinement. So let's start our journey by looking at this sort of common workflow we have in computational fluid dynamics, where we have some model that we want to approximate the solution to. And along the way, we have the physical domain, which will require a mesh. We need to approximate the components of our partial differential equation, the spatial derivatives, the temporal derivatives, and so on. We need to then simulate the flow in some way, and then visualize the results and analyze what we get out of our approximation to our physical model. And in this talk, I'll demonstrate a toolchain that lives inside Julia that lets us do all these steps of our workflow. And I'll highlight that there's a reproducibility repository that you can try it out yourself and run a simulation just like I do during this talk. So let's conceptualize our problem that we want to solve. Let's say I want to do a model of supersonic flow over a cylinder. So I'll decide this is a gas dynamics problem. So I'll model it with compressible Euler equations in 2 spatial dimensions. This is a nonlinear partial differential equation. So complicated flow features can develop over time. Discontinuities in the form of shocks or vortical structures can form behind the cylinder with this supersonic flow that's going over it. I've made a little cartoon of the domain that I want to use, where we have a cylinder and it's placed inside a channel, and the top and the bottom of the channel are sort of wobbly sinusoidal walls. So everything is naturally curvilinear, and we have some physical boundary conditions that we're going to impose. We have an inflow on the left, we have an outflow on the right, and the cylinder and the top and bottom walls will be walls. So that's our problem setup that we've drawn a little cartoon, we've conceptualized, this is what I want to solve. So the first question is, where do meshes come from? I have this curvilinear domain. How can I create the mesh that I need for my numerical solver? For this, we use what we call HOHQMesh, or high order hex quad mesher. Originally written in Fortran by David, this HOHQMesh.jl is a front end to this software. It links us into the Fortran code. And you can use it to create quadrilateral 2D meshes or hexahedral 3D meshes, also with high order boundary information. In addition to that, we've added some capabilities for interactive building of our model of our outer curves, say this outer curve here, or inner curves, and we can visualize them before we decide to send this to the mesh generator and create the mesh. So for this interactivity, we use Makie. And over here is a picture of one such interactive model that I've built. And this is available in the tutorials for HOHQMesh. So first we need HOHQMesh. So the package manager handles all of this stuff. So to install HOHQMesh and the interactive tools that we're about to demonstrate, I just import PKG and then I add HOHQMesh, and boom, I have it all. I can now generate meshes. Because I also want to visualize this interactive model, we use Makie for this. And in this talk, I'll use GL Makie, which is a certain backend that lets me plot stuff directly from the REPL. And that's it, I'm ready to generate. All I needed was these few lines of code. So how do I use it? Well, let's think back to the problem setup that we considered. We drew this little cartoon of the domain, and I already know sort of the bounding points. I've written them here, these 4 corners of the domain. I have 2 sinusoidal walls. I have 2 straight-sided walls. And I have an inner boundary that's a circle. But I can use a little bit of intuition about what this flow is going to look like. I have flow from left to right. And as the flow goes over the cylinder, there will be a region, a so-called wake region behind the cylinder that's going to form that will have interesting flow features that will require some extra refinement. So we're going to target some extra refinement purposefully and tell HOHQMesh that I need some extra elements behind the mesh, or behind the cylinder rather. So let's use this tool. We load in HOHQMesh and GL Makie, and I first create a new project, or a new model project, one can say. So I give it a name, cylinder sign walls, and I give it a folder called out. This is where all of the files that HOHQMesh will create for us, the mesh file specifically, is going to be saved into the out folder. And then it's as easy as creating curves and then adding them into our project. So for example, here, I've created a new circular arc curve that I've named circle. It's centered at 0.60, radius of 0.25, and then it's a complete circle. So it goes from 0 to 360 for degrees in this case. I could have used radians as well. So that creates a curve, and that curve is saved into a dictionary within HOHQMesh. And then we add that curve to an inner boundary inside of our mesh project that's called cylinder flow. I can do the same thing for the outer boundary curves. There's also available, I can use straight lines as my curves that I add. I can use parametric equations. And then I can manually add refinement in this wake region that I briefly mentioned earlier, where I name it wake region. Smooth is, as I transition from these refined elements back to coarser elements, it has a smoother transition. So there's no sharp jumps in how big small elements are with respect to bigger elements. And then I just tell it, where does this line start? Where does it stop? And then its width and the target element size inside that wake region. And then I add all of those components into my project, cylinder flow. I've called it refinement line. And when you do this, you can then plot the project before I send it to the mesh generator. So here we've just added this wake region. That's this dashed box here. The inner boundary curve, I already added that as well. That's my circle that I built. And the outer boundary curve are these parametric equations for the sinusoidal walls and these straight line walls. And notice I've added them with counterclockwise orientation. So I started at the bottom and then I go right, top, left. So this is a right-handed sort of orientation for everything. This is required by HOHQMesh. Once I load all of this into my model, for example, I can get the outer boundary curve information. And I see that my outer boundary curve is itself a dictionary of dictionaries. And it has bottom, right, top, left. And there's some parametric equation curves and there's some straight line curves. And then I can just send this to generate the mesh for cylinder flow. And what pops out is my plot is updated. So now these blue lines, this is the mesh that HOHQMesh just generated for us. In addition, it prints out some mesh statistics so we can decide, is the mesh okay? And looking at the statistics, we're happy with it. The mesh itself generated in under a second, so that's good. And it gave us this domain is now meshed with 436 elements. In addition, this generate mesh call, when I typed that in, it updated my plot. It sent this model dictionary into HOHQMesh and generated the mesh and then updated the plot. It also created a mesh file and a plot file for the mesh that it saved to this directory out that we set earlier when we constructed this new project. So now I'm happy with the mesh and I have the mesh. I've updated my little cartoon here. Now that I've discretized the domain, this is what it looks like. Now I need to rewind again and look at the physics that I'm trying to model, and I need to decide on my solver components. I want high order accuracy because of vortical structures, and they're going to propagate throughout this domain. The mesh itself is unstructured and it's curved, so I need to maintain that accuracy on this unstructured curved mesh. I know that this is a nonlinear model, so shocks can develop. I need a way to handle this shock capturing with this complex behavior. And the solution evolves in time, so the mesh should evolve in time as well and adapt to what the solution looks like. So for this solver, we're going to use Trixi, which is an adaptive framework, simulation framework for hyperbolic PDEs. It's high order accurate on arbitrary unstructured curved meshes. It can do 1D, 2D, or 3D. I'll only do 2D in this talk. And it's integrated into the Julia ecosystem. So it uses ordinary diffie-q to solve, to do integration in time. pforest is the library we use to handle the adaptive mesh refinement. We can visualize using plots or Makie. And for performance, we use loop vectorization. There are many other packages that Julia or that Trixi takes advantage of. I've just listed these 4 here. So very similar to installing HOHQMesh, it was really slick with the package manager. Same with Trixi. We just need to add Trixi in ordinary diffie-q, and we're good to go. We're ready to run adaptive simulations. But how do we do that? It's been a little bit vague up until now. I know Trixi has all these capabilities, but how do I pick and choose and blend together the features that I need out of Trixi to solve this supersonic flow problem that I've posed? That's where this so-called elixir file comes in. This is where we mix together the components of Trixi into an elixir that we can then send in and run. So first step in mixing our elixir, we decided on our model. This was also the first step of our workflow. We take the equations to be the compressible Euler equations in 2 dimensions. In this case, I'll set the gas gamma to be 1.4. It uses the ideal gas law. And the elixir file itself is Julia code. So within the elixir, we can also easily extend Trixi to have extra components, as long as the call structures of, say, our initial condition match what Trixi expects with its existing initial conditions. So I create a new initial condition for this Mach 2 flow over a cylinder. So there's 0 velocity for the Y component, there's 2 for the X component of velocity, and then I set background parameters for the density rho and the pressure P. I can do similarly, I can create new functions to impose my boundary conditions, that I have my supersonic inflow and I have supersonic outflow. So I have my physics. Now I need the domain. Well, we've already meshed it using HOHQMesh, and it's been saved into this file. This cylinder sign walls was the name of our HOHQMesh project, and now it's been saved to this file cylinderwalls.inp. This is an abacus formatted file. In order to load this mesh into Trixi, for convenience, I just call this mesh file where I pick out where it's saved. And then I call pforest mesh, and the 2 means 2 dimensions. And that's it. Now the domain has been loaded into our mesh for Trixi. And we use pforest here because it allows for this adaptive mesh refinement that I'll talk about in a few slides. To impose the boundary conditions, we create a dictionary. And these names in the dictionary match the names that we gave in HOHQMesh when we built our project model. So for example, we had our circle that we added for our inner boundary, and then we have bottom, top, right, and left for our outer boundary that I showed when I ran a little bit of REPL code. And we can immediately assign boundary condition wall for the top, the circle, and the bottom, and then our newly written supersonic outflow and supersonic inflow at the appropriate right and left boundaries. So the domain and the physics are now taken care of. Now we need to decide on the solver. And we know that we have shocks. So we need to build that shock capturing capability into our solver struct, or our solver part of Trixi. To do this, we use a so-called shock indicator. It's called alpha, and it tracks the location of the shock as the solution evolves. And we use this parameter alpha to then blend together a high order method that's very, very accurate, but can have issues near shocks with overshoots and undershoots, with a low order method that is overshoot, undershoot free, but because it's low order, it would kill scales, say, of vortical structures. This is within a special discretization type that's called this volume integral shock capturing. So that's our actual approximation of volume terms. And then we have surface terms. This is how we couple the elements together. And we're building a fifth order method. So we use polynomials of degree 4, and this is a discontinuous Galerkin spectral element method with this blending of the shock capturing. So now we have the physics, the boundary conditions, the mesh, and the solver. And now we've discretized everything in space. So we're going to assemble all of this into a semidiscretization, here called semidiscretization hyperbolic. We combine together our 4 pieces, or our 5 pieces that we have. And we do this because now we can assemble this into an ODE problem and unlock this horsepower of ordinary DiffyQ and let that library solve our semidiscretization in time for us. And it gives us lots of flexibility of picking which time integration method I want to use. During this time integration, we often will need to perform certain actions, such as maybe updating the time step with CFL-based time stepping, saving the solution to a file for later post-processing. Definitely for this adaptive mesh refinement, the solver itself has this shock indicator in it, and it's doing its best to track discontinuities and shocks that may develop during the simulation. But we haven't addressed how is the mesh going to adapt yet. And then we also can add in something like positivity preservation to make sure that density and pressure always remain positive, as required by our physical assumptions and our physical model of the compressible Euler equations. To do this, we use callbacks, which are these routines that can be executed during a Runge-Kutta stage or during a time step, after several time steps. It's just a routine that we can pass to the ODE solver and say, hey, do this, every 5 time steps or every 100 time steps, do something. So I've highlighted here how the AMR indicator is built and the AMR callback. So the indicator for AMR is this indicator loaner. Essentially what this does is it approximates gradients because the AMR indication has a different job than the shock indication. The shock indicator only looks for discontinuities. Vortical structures, although they're complicated, they're smooth. I don't want to activate shock capturing and in turn activate my low order method near the vortices. I want that to be high order accurate. So the AMR indicator is just trying to find where is something interesting happen. That's all it's trying to do. And the indicator loaner does a good job of this. We then send that indicator into the controller because the controller decides when will I refine, when will I coarsen, and how many levels am I allowed to go up or down. So my base level 0, that's what HOHQMesh gave me. That's my base level. And then I'm going to allow this to evolve up to 5 levels of refinement inside pforest or inside the mesh adaptation. And we can also add a medium level 3 that it can hit as a certain target. And then we assemble that into the callback. And here, this interval 1, this means that the AMR callback is going to be called after every time step because this flow is rapidly evolving and we need this capability of the AMR to adapt as well to this complicated solution. Then we have our callbacks. We just need to decide on our solver, or our time integration solver rather. We pick strong stability preserving Runge-Kutta because this is a problem with shocks. And we use error-based time stepping in this case. And we load in this stage limiter for the positivity preservation. So the AMR callback and say the save solution callback, for example, those are step callbacks. So after certain numbers of time steps, this happens. We need to check positivity within each stage of a Runge-Kutta scheme as well to make sure we don't violate physics of having a negative density or so. But we can pack all of our callbacks into a callback set, and then we can solve the ODE using this solve command. And collecting everything into our elixir file, in this case, I've named it elixir Euler Mach 2 cylinder. We can then run it directly from the REPL using Trixi include, which is a special version of include specific to Trixi that allows us to change certain parameters in the elixir file we wrote. For example, I've changed the final time here to be 0.5. Cool. So that runs on my laptop. It takes about 20 minutes to run up to time 0.5. Okay, so it didn't crash. Can we at least visualize this? What's it doing? And that's where we can use Makie in this case to plot the solution that's stored in this variable sol. Sol has the initial solution and the final solution. We've already loaded Makie during our HOHQMesh part, so we can immediately create the plot data that we need, and then we can just visualize, in this case, the density row. And Makie plots our density as well as the adaptive grid. So we see the adaptation is definitely happening. And we know that the physics of this makes sense. I've only run this up to 0.5, so not to the final time that I really want. That we have this bow shock that forms from the front part of the cylinder. We see the beginnings of this vortex shedding in the wake region, and we have additional shocks that are coming off of the sort of sinusoidal walls when this Mach 2 flow hits the walls. So everything looks good, but I'm missing something. It would be nice if I could look at this adaptivity and I could see how this evolves in time. This is where that save solution callback comes in. The save solution callback saves check-in files of the solution and the mesh in HDF5 format throughout the simulation. And then I can use another tool, Trixi to VTK, that will then convert these Trixi output files from HDF5 into VTK format that I can then use in something like ParaView. And along the way, this will create extra files that will also let me plot where is the shock indicator, where's the AMR indicator, how does the mesh look, all of these extra indicators, those are also logged into this save solution step. So when I do that, I load it into ParaView. I've now run to the final time, which was 2.25, and I can watch how this evolves. And we see that the shocks develop and they start interacting. There's these vortical structures are forming behind the cylinder. And here I can pause for a second, that we have these vortices. These are smooth vortices being shed from the cylinder. We have some Mach stems forming on the top and the bottom that are shedding Kelvin-Helmholtz instabilities, but both of those things are smooth. And we see that my shock indicator over here, it doesn't notice, say, the Kelvin-Helmholtz instabilities. It doesn't see these vortical structures. However, the AMR indicator does see them. This Lohner indicator sees that we have something interesting happening in these Mach stem regions as well as behind the cylinder. So unfortunately, the journey has to come to a close. But let's reiterate what we just did. We conceptualized a flow problem, a Mach 2 flow around a cylinder problem, generated the mesh, created a discretization and solved it and simulated and visualized without ever leaving Julia, without ever leaving the REPL. I only left at the very end because I wanted to make a movie with ParaView. The actual creation of all of the results, everything lived inside Julia. And that's what I mean by the journey is now ending. So thank you for your interest in this journey. If you want more information, you can join us on Trixi's Slack. There's also a specific meshing channel, a HOHQMesh channel. And if you want to see more results, you can always check out Trixi's YouTube channel. Thanks again for your attention.